So last time we were looking at a few examples. So we were looking at basically two questions. So suppose we are given m vectors and also this is just an example. So even if you haven't actually been following, this should not be too difficult to tag along. So you can see if things make sense, if they don't, if they're okay, so we're going to basically ask the following question about this. Please, you guys, the numbers are a little bit, I know it's my limitation, but it would really help if you could please stay silent. Okay, so how does one determine if the vectors over alpha are linearly independent? Sorry, I can have a show of hands for those who are following, so I know who to focus on. So, like, just you guys. Is anyone on this side? Anybody else on this side who's following around? Okay. Alright. Thanks. Okay. So the second point is this one. Given feature in F1, how does one determine whether beta is a linear combination or alpha over and proxy was how can one give an explicit extension of subspace W, which is just the span of. I'm very normal, guys. I'm sorry, it's a bit distracting. You can text if you want to know, so it's fine. Okay. So these were the three things, right, that we were trying to look at. These two we had sort of looked at last time, so I'll quickly review what we looked at, and then we'll try to see how to get to the third point. Okay. So the first point is, how does one determine if these vectors are linearly independent? So for both A and B, we have done some calculations, and we found that one can write an arbitrary vector. So suppose beta is some arbitrary vector. We want to be okay. Then so suppose this is there. And then we showed that A beta is a linear combination of alphas and it must satisfy this equation. So these are the coordinates of the vector beta, and this is the condition that we want to set, which is and what is this capital R? So capital R is the load reduced. Additional matrix. Corresponding to A, where A was basically what this is saying is that you're given these vectors. What you do is you write it down as you use these vectors as rows to form a matrix A. And now what you do is you construct the row-reduced echelon matrix capital R corresponding to capital A. So you can do that. And then the condition for testing whether this vector beta is a linear combination of these alpha is or not. You basically check if this condition is true. It's just a condition on the conclusions. Okay, but that was sort of the basic things. You can check whether this vector belongs to this subspace. And similarly, with when it comes to checking whether these vectors are linearly independent or not, you can use this matrix capital R. Okay. So it will tell you, depending on the rank of A, it will know whether the vectors are true. Okay. Is that right?
We saw this someone who had gone out how they can do something great. Thank you so much.
So this is what we have discussed last time. And we sort of stopped here. So this calculation, you can check how this is derived. This is basically just using properties of this, the fact that this is a row echelon. Alright, now we come to, so this is how we do part C and D. Now let's see how to do part C. Okay, so part C, what we're going to do is so the first thing called W is the row space of A. You can chat, right? Just a chat. You use your phones or whatever. Or if you have a question, if you're following and you have a question, ask me please directly. Don't ask among yourselves. If you're talking among yourself, just use text. Sorry. Okay. And the next point is the W is the subspace spanned by alpha 1 to alpha. Right, so these two things are the same. W, remember, is this right? This is this right? And the row space, the definition of row space, remember, is the definition of row space.
Vector space spanned by the subspace of the vector space spanned by the row vectors of the matrix.
Exactly. So this is exactly the same, right? And then the last one is that alpha is the row. These are things row vectors. So this is okay. So I think I already explained this to you when I was explaining how you can check beta as a so check beta belongs to W. Now the question is, what kind of description is this equation giving us? So it describes, what kind of description? This is now we go towards the questions. Okay, so what kind of description is 235? So let's look at it in a little bit more detail. So of course we already said that if you have a vector, you can check whether the vector belongs to the space or not. Now we're going to use the same characterization to see if we can say something more about the entire space. So it describes W as all solutions to the Maybe I wrote which should be homogeneous, I guess. Homogeneous linear equations. Okay. And the system has a special form. It has a special form. So what is the special form? So it basically expresses n minus e to the power coordinates. Okay, so it's specifying these bj's, which are I did not get the index what you did. So here j is going from so it specifies n minus r coordinates in terms of as linear combinations of r distinguished coordinates. And what are these distinguished coordinates? These are the dk1 to the okay. So remember this ki. Do you remember the definition of ki? So ki was just this way. Just the first non-zero entry in our 0 that's 1. So this is k1, this is k2, and so on. So it's the column at which you get the first non-zero entry. And what this thing is saying is that if you look at this carefully, what it is doing is it's expressing all the coordinates in terms of these special coordinates, OP, at these locations. In terms of those coordinates, all the other coordinates are specified. So as a system of solutions, these solutions have this special property that these coordinates are going to fix all the coordinates. Yes, I guess the questions are here. If we keep asking others. Now, one has complete freedom there. We specify these coordinates. We specify that is, if you have, say, C1, C5 as your class scalars, then specifying BKI is C1 specification. That is what it is. Okay. So now, the main point is the following. So given alpha is, one can reduce and get. This is stuff I just told you. I'm just writing it down so it's absolutely clear. So one can get capital R is a reduced echelon form, and the scalars are equal. Can be used. This is what I described as the more good. Now, the next point is that every subspace W of Fn has a description of the form. Okay, so this equation basically it answers this question C as well. That's all it is saying, right? Because to extend the subspace, you're saying that it is just a collection of vectors whose coordinates are special. That is all it is.
Sir, what will be the value of pki if a certain row is 0 in the reduced matrix, reduced echelon matrix? Because there is no non-zero element at all.
Yeah, so those vectors are free anyway, right? That doesn't.
But sir, then how will be, beta will be obtained if we will multiply pki with every row?
You're saying so the question is, so you're asking, suppose you have some non-zero rows. What you're asking is, suppose the vectors are zero.
This is suppose the last row is 0 or the second last row is 0.
So suppose the last row of capital R. Of course, because you won't start with the zero vector, it's only when you write the so the last row of capital R is 0. Okay. Then what is the question then?
So what is the value of pki for that row vector?
What will be pki? So that's a good question. These big arrays, you see, index I is going from 1 to little r, and little r is the number of non-zero rows. Because you only have to kind of.
But sir, then every element will not be obtained of that beta vector because there are certain elements that we have not multiplied in the row vectors and they will not be obtained.
Right, so you can just apply the condition. See, the constraint is not on the jth coordinate. So j can go from 1 to 1. The constraint is on these conditions that are being used. So if, say for example, it's just a linear combination of certain conditions. Just that the constraints from those final rows will not appear when you're specifying the certain. That is all it is. The sum of all right, for fixed j, the sum of all. Is that answer?
Sir, I am not able to understand that Bj will not get formed if for example, every jth column is 0, we will multiply the pki element to that and we will get 0 again. So it will not be Bj. Sir, I guess when you will take a matrix except identity matrix, this equation will not follow there.
Yeah, maybe I'll give you some examples to work with. Or maybe I'm missing, I'm not fully understanding what you're asking. We can discuss it afterwards, but very quickly we'll do one last attempt and then we move on. So suppose this is the vector, right? That has 0 entries. So if you want to look at, say, suppose your vector was b1, b2, b3. Okay, and we want to look at, say, the b3 and b3. And what this vector should be, whether this belongs or not. So b3 should just be a sum over all of the bki's. So this is b1, b2. So that will be b1 times 1 here, so that's right. Plus b2 times 1. So b3 has to be exactly this. That is it. Then the other ones are all zeros.
But sir, R0, Rij element R03 is 0. R03 is 0, so dot 1.
Rij, as we look at the higher the other one, the j of R is a medium vector. So let's see. So the j of column. So then when you're just getting the constraint that this has to be clear. Then you get the constraint. Whatever it is, it gets fixed. That's all I was trying to say.
So suppose that B3 is not 0, B3 is 1.
So then it will not be a part of the vector space, right? It is a condition, right? You're checking the condition. Okay. Yeah, that's the whole point, right? It's like not all vectors will belong to the subspace. It's a subspace. Any other questions? Someone following on this way? Any other questions? Okay, so what I was saying is that this third question is also answered by this equation because not only can you use it to check whether a vector satisfies the condition, you can also use it as a characterization of the space itself. You can say it is the set of all vectors whose coordinates satisfy the condition. right? So that gives you a very clean characterization. Just give me a second. So this is where we were. And now let's continue. Okay, so I'm going to erase this part. Just making it illustrative. Alright. Yeah, I think the remaining things I will leave for you to look at for the test. I think the rest of it is very sufficiently straightforward. I'll add some exercises. So this is, I'm basically working on the part of the in section 2.6. Okay, for those of you who are already. This part. And now let's maybe look at a few concrete examples. Be the subspace. Subspace of spanned by alpha 1 equals alpha 2 is 0 to 0. Now that's so we're just looking at one explicit example to basically make sure we're for the words. So the first step that we want to prove is prove that alpha 1 alpha 2 alpha 2 form basis. The second part is if so what are the coordinates? What are the coordinates of beta? Relative to alpha 1 and alpha 2. Okay, so we're basically just practicing all the concepts that we looked at so far. Part C is that alpha 1 prime. Yeah, let's actually do part by part. I think it's easy. Let's do these two parts first and then we do the next parts. And this is sort of the condition that we really care about. So let me get the concrete here. So dj is sum over time. dj okay. Okay, why don't you check if you're getting everything in the recording on the because I know a lot of you guys are not following and probably will leave it here. Great. Okay, so let's answer the first question. So what we do is, okay, so who wants to tell me how you would approach the question based on all the discussion? So first we have to set up the matrix A, right? So the matrix A, remember, was basically just alpha 1, alpha, yeah. Right? So what should matrix A be? given that sigma alpha 1 alpha 3. Who wants to tell me? Good.
So the first row will be 1 2 2 1.
1 to 1.
The second will be 0 2 0 1.
0 to 4.
And third will be -2 0 -4 3.
There is a clear diagram why that is the case. Okay. Alright. The now what we'll do is yeah. Okay. So now we want to make the derivatives. Okay. So derivatives. Okay. So this I'm not going to ask you to do explicitly, but it turns out that you can convert this by a forward operation into the following operation. Zero, one, zero, 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 zero. Can one get the back please stop the door again? Could you please stop the door? Thank you. Okay. So this is the form, right? Okay. And what we want to do is okay, so A is let's say so you apply some derivative operations on A to get capital R. So the text also tells you what this Q should be. Okay, the way you get this Q is you apply the same operations here, but on an identity basis. So when you do that, your Q under the same operation. So that is the operation. So you do the same thing. You're going to get 6 minus 6 0 minus 2 5 minus 1. So we'll see why this is used, but I also want to know why this is used. So let's see. Okay. So part A says what? So part A is asking, we have to prove against forms and bases. Okay, so whenever we have to show something from some bases, there are two things we have to check. Okay? So we have to check that it spans the space, and we have to check that it's linearly independent. So the first part is true just by definition, because it is the span. Okay? So it only means to check whether they are independent. And to check that they are independent, we look at the row reduced matrix. The row reduced matrix has no zero rows. That means that all of these are linearly independent, because linear independence stays invariant under elementary operations. Okay? Okay. So this part is true. So the answer here is clearly R has rank 3, right? And so now go on, alpha 2, alpha 3, linear. Okay, so that's the first part. Then basically just doing exactly what we did in the general case, like we were just showing you an example set of the concept. So now the question is, so the second part will ask you which vectors, right, are in this vector space. So you have that's what we concept. And now we need to use the I was trying to do it from the other vector. Let's the text, the example I have written is going to a slightly different way from what we discussed. I'm just checking what it is. Give me a second. Let me see. this, I think I will have to introduce some general discussion before we. Yeah, okay, let's skip to a little bit of the discussion. So. Okay, so I think what is probably relatively straightforward to check. We can simply write down the conditions. So we can write down these conditions explicitly at least. And there is some discussion that I need to introduce. So let's write down whatever we have covered, and then I'll tell you the general discussion, and then we'll come back to the example. So I messed up a little in trying to be able to work on it. Okay, so yeah, so this we can write down explicitly. Right? So we have so V1 is going to be what? It is going to be so it will be Vj. Right? So this is going to be over P A I R. Now this is going to answer some more of the algorithms. Right? So let's write it down. Who wants to tell you what this means to? Anybody? You want to? I'm just asking for the evaluation. Right, so okay, so let's maybe write down the case. Right? So K1 is what? K1 is like the the first entry of the row where the first column where a certain row becomes 1. Right? So K1 is 1. K2 is 2. K3 is 4. 1, 2, 3. Right? Not 3. Right? Okay? And now what are we going to do? We're going to basically sum this object. So let's do that. So for the first column we have K1 times Ri1. Ri1 is what? So here's the solution. So Ri1 is 1. Right? Plus Vk2 times Ri2. So I'm now looking at the ith row, then the next row is 0, and the last row is 0. Right? This is going to be 0 plus. Is that okay? Okay, and V2, what is the answer? That's it. So it's for Vk1. Or Vk1 was what? Vk1 was 1. So you get so this is going to be 1 equals B1. Okay, I'm actually a little bit silly. Why was I silly to put Q B1 first of all? I was silly to put Q B1 because BK1s, remember these were the so BKIs are the ones that are arbitrary. They fix, once you fix them, they fix all the other quantities. So B1, B2 and B3 are completely free. So B4 are completely free. We just have to Q B3. Right? Okay. So B3 will be what? Q B3 will be sum over that. BKI R of 3. Right? So now we have to look at the third. The third column. Right? So the third column is this one. And the only entry that will contribute is the first one. So you get 2 times B2. That is the only constraint. This is the entire. So your vector is going to have this one B1, B2. Instead of B3, B2, B3. Because anyway,
can you once explain the point that if R has rank 3, so power and all are equally independent? Talk about that.
Linear dependence? Okay, so this is just saying that what is easiest to so this is basically using results from chapter 1. So the idea is that if you have two matrices, say A, that is rho A equals to B, right? So the number of independent vectors will not change, right? Because you're just taking linear combinations in more directions. It's important, right? Like so, using equations A, you can produce equation B, and then using equation B, you can produce equation B. So anything. So if there's a bunch of vectors that are linearly dependent here, they will also be dependent. So essentially, you can show that the number of independent vectors are going to be the same. Because I forget any one, there's going to be probably also shown that the rank of the matrix remains preserved under elementary operations. Something like this. I forget the exact statement, but that's the basic idea. Okay, so to check whether these vectors are linearly independent or not, you just take you use the reduced testing matrix, row reduced echelon matrix, and then the rank of this will be the same as the rank of the original matrix. So rank of A is going to be the same as rank of B if A is equal. But that's what we use. Okay, so this sort of answers part B as well. So we have like an explicit description for the matrix. Now there is a question about expressing the coordinates of beta relative to the coordinates alpha as power to the alpha basis. Tell me. Okay, so if you have so now the next part for this question, which is when you sort of introducing all this tree, was because we wanted to understand how would you express the vector beta. So right now it's these four coordinates, right? Beta, B1 to B4. We want to express it in terms of linear combinations of class. And how do you do that? So there was a general discussion which I skipped, but it's okay. Let's just work through the example and hopefully this will be clear. So hopefully is this part. I think you understand what the question is. Okay. So now what we want to do is we want to attract so we want to express given by rho 1, rho 2, rho 3, rho vectors. Capital because the subspaces are the same, if you don't know reduced, elementary operations, right? So the row space remains preserved. This will include classing, so we call row space of A, which is the same as the row space of the reduced. This was one that the other would be like the last class, which is right? So this is right. And now what we want to do is, so we write capital R. So we found this matrix. So we're writing each of these rows as 1, this we call it, right? Okay. So this is what we're doing. So we have the basis. Yes, we have the basis for W in terms of these operators. And it's clear that the span of row 1, row 2, row 3 consists of vectors beta subset which equals 21. Okay? So why is this statement true? So then what is the statement saying? The statement is saying that the span of row 1 to row 3 is basically just a bunch of vectors that satisfy this condition. So beta is, remember, beta is B1, B2, B3. Okay, we did exactly that calculation just a moment ago, right, to argue that the third quadrant is vectors. And that was exactly the criteria for belonging to the row space. So it's clear that any vector that satisfies this condition, B3 is to B1, is going to be in the span of row 2. Okay, so now we take such a vector. So it says such a vector. Such beta, which holds that beta is B1 row 1 plus B2 row 2 plus B4 row 3. So you're taking linear combinations here, and yeah, this step maybe is not all that clear at this point because there's still some discussion. Yeah, we're gonna have to prove this later for you, but so let's sort of take it for as an assumption. Okay, so this is we'll take this as an assumption. And I'll probably add an exercise so you can sort of do the key point here is that you write beta, you fix the coordinates the way we described here. Okay? And then these objects here are basically just this is a you sort of use it already actually. Okay, this is the so once you fix the BTIs, you know what the linear combination is. Okay, this part I skipped, I'll either prove it or I'll as an exercise. So this is sort of, so I'll just say, maybe not an assumption, let's say this is that beta is so beta in W, what can write it as and now we're just using this thing. Is that yeah?
Sir, B1, B2, B3 are just random constants we choose, right? So
yeah, it's an arbitrary vector.
So we can just say that beta will be a linear combination of the non-zero rows in the row H form.
Yes, yes. The question is the other way. The question is, if I give you a vector beta and I tell you that it belongs to W, the question is, can you write it in this in the basis of in this basis? That is it.
So we found out the constants from this beta calculation in B part, right?
Yeah, we found, so we knew that the BKIs are arbitrary. We could have chosen the BKIs to be arbitrary. But the remaining B's, so BJ's for J not equal to BKI, not index. Okay, so for any index, so for any index J that is not because you look at all the KI indices for any J that is not in that, those are going to be in terms of these BKIs. So what was the question then?
They will automatically satisfy the conditions upon writing them as a linear combination.
Yeah, so the thing is that you would be able to write it as a linear combination. Otherwise, you won't be able to do it. And then there is this thing that if you do write it as a linear combination, this is the linear combination. Any questions? Why the one person was following? Are you still following the one? Right. Any questions? Okay. So this is what we have now. So just using this thing, we can express beta in terms of this linear combination. Okay, but we're not done yet, right? Because we have to express it in terms of in the coordinates, right? So this just says that the vector beta can be written like this. We have to get the coordinates for this relative basis. So how do we do that? Well, of course, we know how our rho and alpha is related. They are related by this transformation, right? So the rows of A are related to the rows of R by this transformation capital, right? So that's what we're going to use now. So let's just write this in terms of matrix. So we write B1, B2, and B4. And then multiply with the capital. The capital R is the so there's this matrix multiplication. It's not a way to do it. And capital R we can substitute with. So you remember we want to go back to this basis, right? The basic algebra. And remember A was so this will be 2 times right to go from basis beta to the basis beta to basis rho to the basis alpha. Okay, so we do this substitution and then this will basically give you the formula. So it will give you x1 alpha 1 plus x2 plus x3 alpha 2 where so basically this part b multiplied by q is the axis, right? So this is the part of x1 and x2. And now if you do this calculation, because now we also have this matrix Q, right? And remember the matrix Q is exactly basically the same operations that we applied to convert A to a row reduced echelon form. We apply that those same operations on identity. Okay? In order to get, yeah, so maybe I wrote it wrong. So apply it on identity, and these are the same methods. Yeah. Okay, so if you apply the same operations on identity, you will get the matrix Q. So now we just have to multiply this matrix Q with these x's. So x is I just want to check basically gives you the following equations. So it gives you x1 is this gave multiplication. Here is nothing very complicated, but just so that it's easy to grab. Obviously, the actual calculation is not so important, it's just a concept. Okay, so that is the answer. So if you have an arbitrary vector beta, that can guarantee it lies in the this W subspace, then you can express this in the basis of the vectors that span the subspace explicitly in terms of dimension. Okay, so that is some the two parts that I want to cover. Okay, so those were so we did parts A and B. Now there's parts C and D, so let's maybe do that as well. Just to yeah, give me just a minute. Let me check if we actually covered this theory on this. think even if we haven't covered the theory, I'll do the same thing. I'll write it clear in case there's something we missed. And then so I have the last part now. Yeah, we need at least these parts. Alright. So part C says if alpha 1 prime, alpha 2 prime, alpha 3 prime being common vectors, it is 1, 0, 0. 0, 0, 1. How does the whole thing okay, so now we want to show that after 1 prime, alpha 2 prime, form basis. Okay, so that's part C. And part D is if beta is equal. Yeah, okay, let's take the question. So what is he saying that it is asking a similar question, it's now giving you a different basis and it's asking whether a bunch of different vectors and it's asking whether this is a basis for W or not. So how can you check it? So what is the text says? The text says that clearly the vectors alpha 1 prime, alpha 2 prime, are all of the form y1, y2, y3, y4 with y3 equals to y1. Okay, so the third quadrant is twice the first, third quadrant is twice the first, third quadrant is twice the first. Why are we testing this? Because we want to show that something is a basis. So we first need to show that it actually spans the set. And the first step for that is that all the vectors that I'm describing should at least lie in the subspace. Right? Because of course if a vector is outside the subspace, then immediately we know that it's not going to span because it's outside. Right? Okay. So we know that the vectors actually belong to the subspace. So that part is okay. So this implies that alpha 1 prime, alpha 2 prime, they all belong to that. Okay, this is just using the condition we did. So that's the first thing we want to check. The second thing we want to check is independence. Okay. And independence is apparently easy to check by this expression. Independence. If you want to do it formally, you could write the row-reduced echelon matrix, or you could just eliminate the free variable and use. Okay. So independence is essentially created by this expression. So let's check what she was. She was use the question. Okay. So that answers the part C. And now the final part. The final part is a little more involved. A little bit more. Yes, we can get this second one. So the final part is what? The part is if beta is in W, then W is the form that we are using. So remember alpha and alpha prime we had written earlier. So alpha prime is over there. Say the alpha was agnostic. So this is called alpha was Right, so now we look at this part, and what is being asked is, suppose there's a vector, so you're given that there's a vector in that subspace, and you're asking what is the coordinate matrix for this vector relative to alpha and relative to alpha. Okay? And alpha and alpha prime are both. And we already established that they are both bases. Right? So we established that this is that this spans the space and is linearly independent. We also established this spans the space and is linearly independent. How do we check that this spans the space? By checking that condition that we had written. And then we check linear independence either by inspection or by making the right? So those are the two things we want to check. So we do know that they are bases. Now we want to express this vector in modular down coordinates for both of these bases. And how to do this? Okay, so matrix P is defined as follows. So it's defined as P1, where Pj is alpha prime J relative to this. So what we are doing is we are writing the coordinates of the vector alpha prime relative to the basis alpha. Okay? And then just stacking them into columns. Is that okay? It's this notation I don't know if you remember. So this notation is basically going to take a vector as an input, and then when I name the basis, it will tell you what are the matrix with the components. So this is feature of being that you can write. So suppose feature was like 1, 0, so it's a 1, 0. Okay, so this was feature, it would be like alpha prime J, it can be written as 1 times alpha 1 plus 2 times alpha 2 plus 2. That's what it means. Okay, so we're just connecting these coefficients into a matrix. Is that okay? So that's the first thing we did. And now it says that the equations 236 tell us how to find the coordinates. How to find alpha 1 prime. How to find the coordinate matrix. So what was 226? I think I erased it. So 226 was basically this. We had x1 equals, some combination of x1 and so I had written like much of it. So something in terms of these. So this is what is equation. Okay. So basically each of these vectors alpha primes are given to us, right? So we know all the coordinates on the standard basis. Using these coordinates, we can compute. So we can plug them here and this will give you the x's. Right? And these x's are exactly these coefficients. This is x1, the eliminator is x1. Let me know, okay, if you're getting lost. All we are doing is we are saying that you have the vectors alphas, which are already fixed. In the previous calculation, we showed that for any vector that belongs to the span of those alphas, one can construct the coordinates x1, x2, x3, which are basically just this, in terms of the vector that was initially given. Right? Is that right? Alright. So using this process for alpha 1 prime, alpha 2 prime, alpha 2 prime, one can actually construct this in HSP. That is all that is. And so you solve this for each one of the choices of alpha 1 primes. Okay, take a minute. This is not clear enough. So assuming this is clear.
Sir, just a second. Sir, in this proof, you showed that every element, every linear combination of alpha 1 dash, alpha dash, and alpha 3 dash belongs to that W. But you didn't show that every element that is in W is in the span of alpha 1 dash, alpha 2 dash, and alpha 3 dash.
Yeah, that is a good point. But the point is that these vectors are independent, right? So there's 3 independent vectors, and so that would basically mean that you have. Yeah, they're going to span the same space, right? Because the dimensions are the same and those 3 vectors belong in the same vector space. So if you, I think that there was a theorem, right, that said that regardless of which basis you pick, it's going to span the same space. So if you have 3 orthogonal vectors, I think there's a lemma. What you're saying is correct. It's not immediate, but it uses one of the previous results that said that if you can always extend the basis. So if I give you say 2 linearly independent vectors in a subspace, you can construct more linearly independent vectors until it spans the whole space. And here, since we already have 3, right, like you can't do more than 3, so it has to span the space. But you're right, like it's missing an argument. That's a good one. One should be more careful.
The vector space by definition will contain all of the linear combinations of the vectors it contains, right?
Yeah, but it might still be smaller. That's
So
what
that was in the earlier statement. Every linear independent
Right.
Set of vectors will be a part of the basis. So there are 3. It can be more than 3.
Yeah, but the point is that you already know the dimension of the space. Right? You know that
Dimension is 3.
the W, yeah, the dimension is already 3, so you can't have any more. So it's the biggest set. It's basically one of those results. Like, can you get confused with precisely which statement? Any more questions? Okay. So let's continue then. Okay, so it turns out that yeah, so if you do this calculation, there's this one can check. So if you do some calculation, you will see that alpha 1 prime turns out to be alpha 1 minus alpha 2. So these are the coefficients, right? You can find the coefficients for each one of them. And so when you do a calculation, you will see that here. So basically it's x1, x1, x2, x1. So you can calculate that. You put these coefficients for alpha 1. Let's say there it is. Alpha 2 prime is equal to alpha 2. And alpha 2 prime is equal to alpha 1 minus alpha 2 plus alpha 4. Okay? Alright. So then using this one for constructing HSP as surface. So the HSP will be 1, 0, 2 minus 1, 1, minus 2, 0, 0, 1. So now we answer the same. Yeah, okay, so that essentially solves the question. Right? So we wanted to know how to express. Yeah, I don't know why I actually put it. But this essentially solves the question already. Because the question was how do you express beta? Okay, so if you have some arbitrary vector beta, how do you express it in terms of x? But in terms of x, right? And this is telling you it's in terms of in terms of alpha, you can solve these equations and you give you the x's. And then if you want to transform from x to alpha prime, you can use this linear combination. So you just multiply it with p and then. That's okay. So the text also discusses another way of answering essentially the same set of questions. It's called the second method in the text, where I think now once the projector works, I think we can tell you alright, so now we can start the next chapter. So now we finish quickly. Start section 1. Linear term. Alright. So let's start with, there's a lot of, I wish the slides were working. So what we're going to do now is we're going to introduce linear transformations, and this is primarily what we're going to study for the rest of the video. And so let's basically just start with the definition. So we're going to the motivation that will come here. Just as the motivation for studying row operations is not immediate until you actually start looking at vector spaces. So similarly, the motivation here will look a little bit unclear, but as we go, we see lots of important transformations falling into this category of the transformation. So what's the definition? So let V and W be vector spaces. Over the field. What is the definition? It's saying that it is a transformation. So you give it two vector spaces first of all. So there's some vector space V, there's some vector space W. A linear transformation is a map from V to W. So you take vectors in V and map them to vectors in W. And it has the following property. Okay, so we're going to denote it by T, and this T has the following property. So you put any two vectors in the initial vector space V, multiply the first one with some scalar. Okay. It will give you, it must match the following. You take the vector alpha, apply the transformation, multiply by C, and you take the vector beta, apply the transformation to any other. This is the definition. Now, you might see some resemblance already with how we defined. So, like the condition for being a subspace, it was already that you take any two vectors in the subspace, then you take C times alpha plus beta, and that should also belong to the subspace. So you can see that there are structural similarities in how the definition is used. Okay, and you will see that these things they watch it over here. So now let's try this. Again, so let's look at the example. So the first example is if E is any vector space, so not any vector space, then the identity transformation defined as I actual alpha is your alpha. Okay, so you take a vector, you apply identity, does nothing. This is the most trivial thing you can think of. Okay. Is A. Why is that? You just remove the T limit. Obviously, there's nothing to do. Okay? That's right? Okay, so that was one. So this is the identity. The other example is the zero transformation. Okay, so now how would we define the zero transformation? on alpha which is 0. This is also zero. Very good example.
Zeros of different matrices, right?
Yes. Okay. That's good. So 0, this is like a function. So you can have like 0 active on alpha.
Sir, isn't it from B to B? मतलब the domain is B and the codomain is also B?
We did not make that.
But sir, because 0 dot
For identity, yes, that was the case. But for the other thing, we didn't really make this.
But sir, 0 dot alpha will be in B itself because 0 is a part of the field.
Yeah, but I'm not saying it's the product, right? I'm saying that if you define a map, you could potentially define it to be a matrix. At least that's what I think the text is doing. What you're doing is correct as well, right? If you just multiply with 0, that will certainly be a.
So also, since the function is just a mapping, it need not be necessary that the vector we are taking for the zero transformation is also 0.
Yeah, that's true, yeah. So we are taking any opportunity that happens.
And the other can also be.
This is just a name, right? You can call it. That's just normal. It's just suggestive normal. Okay, just like identity, you can call like this is that the name is suggestive. That's what we use. Any other questions? One. Okay. So this is fine. Now let's look at more interesting examples. These are really short examples. So let's look at example 2. So example 2 says the following. So it says let capital F be and B be the space of polynomials from capital F given by f of x equals to 0 plus 0 So we are saying that consider some field F where that's fixed. And now we need to define B to be the space of all polynomial functions that are going from F to F of this form. Okay, so it's not an infinite polynomial in the sense that there is some maximum k. And this is the form, right? It's a general polynomial. We proved already that this actually forms a space. So this is that part. And then let df, this is a map. So df is the familiar differentiation map. So what we are explicitly defining it to the following. So you move C0 and C1. Yes. And you guys, come on, you can even automate putting your phones on silent. There's no reason for this to happen. C2x plus K0. It's a differentiation, right? It's just by definition. And then T is here. It's a linear transform. From B to taking polynomials to polynomials. Okay. And let's quickly check that this is actually the case. So why is this the case? Yeah, I'll probably leave it as this. Right? Because if you add polynomials, you're basically going to, like, it's linear, right? So you're basically going to add the coefficients. The x is going to act essentially the same way. So whichever way you compute the coefficients, it doesn't matter. If you do it twice and add them, or you add them first and then you apply the transformation. Yeah. The only thing that's making a difference is the coefficients getting added, which will be the same. Here you're just multiplying by 3. So it's going to be, you can check. So that's the first concept of example for you of linear transformation. Okay. Now let's look at number 1. So the other one is the example 4 here, so there's a P of x and cross x. So you can use it. And let Q be of x and cross x. Again, over so P and Q are just matrices. Here, we are going to define the function T from f plus n to itself by the following. So you have T here. So T is defined as P A. And we can check that this is well defined because A is n cross n. Okay. P is n cross n. So this is n cross n. And so everything is consistent. Okay. And yeah, if you define such a map, then T is a linear transformation. Because the following pictures, so we have T sequence A plus B. This is a condition we want to check, right? We want to be able to write this object that one. So we're going to apply the definition and then we're going to massage it until we get the right form. And that is going to be relatively straightforward since instead of being rounded on the condition of so far I'm just applying the definition. This is CA plus B. The map says you multiply on the left or right by Q. So on that. Now it's matrix multiplication, right? So I can write it as C PAQ plus PPQ. Right? I'm just expanding the matrix multiplication. And then this clearly is C plus right? So satisfies the we have 4 minutes, so let me do the last example, I think. So first one, capital R, give the field of use. The space of capital R to capital R. That is continuous. So we are basically looking at the set of continuous functions. So now we define the transformation T as follows. So T f actual of x is the same as sorry, it's defined to be just the integration from 0 to x of the function. And the thing is, so it's all it is, right? T here. Okay. And then why this is true is basically following from linearity of integration. This is linearity of integration. So one of the fundamental properties. Okay, so this basically tells you that the structure is very general. There's lots of different things that we don't think of priority have any common structure, but it turns out that they all satisfy this property, and we want to speak about these things. So thank you.